Hey guys, welcome to 15 to 51 Weekly Review. We're going to be doing chapters 10 and 11 today. So a couple of disclaimers. I'm not going to be going through everything in the chapters 10 and 11 because there's a lot of problems in there. And there's like a lot of exercises and stuff, and you should definitely still read the notes. But what this will be is it'll be like kind of a crash course on chapters 10 and 11, kind of the most important things. And I'm going to try and summarize some things and maybe put more details into places where I think appropriate. But I do highly recommend that you either watch this video to completion, beat on 1.5 times speed if you want it to be, or read chapters 10 and 11 in the Diderot textbook again before Thursday's lecture, because I really think that would help you follow along. In the future, these weekly reviews will be interactive, and we'll still post the links, but for this time, we're just going to pre-record this, and you guys will be able to watch on your own time should you want to. Cool. So before we get started, right, we're going to be talking about the P versus NP problem. Maybe let me just motivate why this is, in my opinion, the coolest topic in the entire course and why it matters and why it should matter to you. So specifically so far, we've been talking about in this class so far, we've been talking about decidability, computability. Are certain problems solvable or are they not solvable? But when they are solvable, we kind of just stop there. We don't really care how efficiently solvable are they. Is there any algorithm out there? But now what we're going to be doing is we're going to be kind of looking at these finer grained buckets to classify problems into. So specifically two buckets that we'll be caring about right now are P and NP. And there's really kind of two branches to theoretical computer science, two main branches, I would say. And on one hand, you got the algorithms guys, and on the other hand, you got the complexity theory people. And these two kind of work hand in hand. So what the complexity theorists do, and what we're doing is basically a tip of the iceberg intro into complexity theory. What the complexity theorist people do is they'll kind of take a bunch of different problems and they'll relate them to one another, and in pretty amazing ways, right? Because they can take problems that seem maybe very unrelated at first glance and connect them somehow and put them into buckets and say, oh, these have these properties, etc. Then what the algorithms people will do is they'll kind of take one of the problems out of that bucket, they'll study it, they'll come up with a good algorithm for it, and in the process, not only are they coming up with a good algorithm for that one problem that they've been studying, but sometimes it can have a domino effect, and it can really, affect a bunch of other things that are in the same bucket or similar buckets. So maybe that explanation doesn't make so much sense right now, and it's kind of confusing, but the whole point that I'm trying to emphasize is this is the part of 251 where you really see that computer science is really a science. And maybe I'm getting too excited about this, but let's go ahead and get started with the actual material. Cool. So like I said, this is going to be chapter 10 and chapter 11. So it's basically P versus NP, polynomial time reductions and non-deterministic polynomial. So cool. Let's talk about what these two buckets really are. So first of all, P, this is the set of all languages, right, that can be solved in polytime. Cool. NP, this is the set of all languages whose solutions can be verified in polytime. I apologize, I can't really write much faster on my iPad, guys, so if you want to put this on 1.5 times speed, I wouldn't be offended at all. Cool. So NP, this is not the formal definition of NP. We will get a formal definition of NP in a couple of minutes, but for now, I just want you to kind of have intuition about what NP really is, right? It means they're the set of languages, maybe you don't know how to solve it in polytime, but if someone were to give you a solution, you could quickly tell that it's a valid solution or it's not a valid solution, right? So a good example of something in NP is Sudoku. Sudoku, I think that's how you spell it, right? If I were to give you a half-empty Sudoku board and said, hey, can you solve this for me? It might be difficult to do so. But if I were to give you a half-empty Sudoku board and a completely valid Sudoku board, fill out the rest of the squares, right? You could quickly be like, okay, looks like every square has the numbers 1 to 9 in it. Every row has 1 to 9. Every column has 1 to 9. Cool. This looks like a valid solution, right? So NP doesn't necessarily mean you have to be able to solve the problem in polytime, but if someone gave you a solution, then you could quickly be like, yeah, that seems to check out, right? So the million-dollar question, and I literally mean the million-dollar question, is P equal to NP? So what we know right now is we know that P is a subset of NP. So every language in P is also going to be an NP. Cool. This should kind of seem intuitive to you, but without the formal definition of NP, it's hard to see why that might be true. But take it for granted for now until we get to the formal definition of NP. What we don't know, what nobody knows, in fact, is whether NP is a subset of P. If this is true, this would mean P is equal to NP, and lots of things as we know it today would break. But I personally think that P is not equal to NP. So my opinion is that the two things are separate. So my opinion is that the universe kind of looks like this. This is the picture. The real question, like this question here, is equivalent to, is there anything in the shaded region? I think that there definitely are some things in NP and that aren't in P. But again, that's not something that anybody's been able to prove so far. So still $1 million question if you can prove it. Cool. So the reason I think that is because think about what NP really is. It's like the set of things that like you can just look at a solution and be like, okay, that solution checks out. See, just because you're able to like look at a solution and be like, that seems right, doesn't mean it should be easy to come up with, right? Like if you've ever had a hard homework problem, right? Maybe this is a facetious example, but like if you've had a hard homework problem and you've been like, oh, I have no idea how to do this question, and then someone shows you the solution, then obviously in hindsight, like it's, oh, that wasn't so bad. But does that mean that like you would have been able to like come up with it like quickly yourself? Maybe not. Cool. Again, there's plenty of things wrong with that analogy, but just for the intuition, that's kind of what we're talking about here. Whether being efficiently verifiable solutions implies you could have come up with this solution yourself quickly. Cool. So this is a high level what P versus NP is. And before we can talk about a lot of the cool content in this chapter and in these chapters, we have to kind of develop a little bit of machinery first. So the machinery that we have to talk about is we have to talk about reductions. So first, I'm just going to kind of draw this little thing here. We're going to have two worlds. We're going to have the decidability world, and we're going to have like, I'm going to call it the efficiency world for lack of a better name. Cool. So earlier we had two things like A and B were languages, and we could kind of relate them in terms of like their decidability-ness with this symbol less than or equal to. This was our tool. So we could say that like A is less than or equal to B, and what this statement would mean is that if B is solvable, then A is solvable, right? So specifically what this is saying is B is at least as hard as A. That's kind of like the intuition. So similarly, like now when we're talking about like, I don't know, like polytime or like trying to put like problems into buckets based on how efficiently they can be solved, we care about more than just like, oh, if this is solvable, then that's solvable, right? We kind of want to like relate things in terms of like, if this is solvable in polytime, then this is also going to be solvable in polytime, right? So we want to have a statement of that form. So if we have languages A and B again, we're going to have different tools. Specifically, our tool is going to be denoted like this. We're going to have two actually, and I'll explain the difference in a second. So this one's going to be called a Cook, and this one's going to be called a Karp. And you might notice that the background of this is a Karp Cook. That's just a little joke. Don't worry about that. Cool. And basically, we want to be able to kind of come up with relationships between languages of the form like, if A polytime reduces to B, this is the sentence that like, if B is solvable in polytime, then A is solvable in polytime, right? Now that we care about efficiency, we want to have these qualifiers on the way that we kind of compare languages to each other, right? So you might recall that in decidability world, right, it was really nice to have this reduction as a tool because at the very beginning of like Turing machines, in 1936, Turing was able to show that Haltz was undecidable, right? And he did this without any form of like reductions. Reductions are kind of like a way to compare two languages together, right? And he did this kind of directly. He gave this direct diagonalization kind of argument that Haltz was undecidable. And once he was able to do that, right, he was able to kind of show that a bunch of other languages were undecidable by showing that they were at least as hard as Haltz. And then like all these languages are undecidable. Now, that's awesome, right? All of these languages that are like greater than or equal to Haltz are at least as hard as Haltz, so they must all be undecidable too, right? That's awesome because now we didn't have to show a language is undecidable, we didn't have to come up with like a out of thin air diagonalization proof for that language. Instead, we could kind of use this kind of like, I don't know, comparison tool, right? This comparison tool of like what we call a Turing reduction. I'll write it here. Cool, so that's awesome. Now, in the efficiency world, we want to have something kind of similar, right? Maybe like we show that one language, let's say, isn't solvable in polytime. So let's let like L be like some language not solvable in polytime. Right? If we have some language L that's not solvable in polytime, and then we say that L reduces to K, polytime reduces, which reduces to like M, which reduces to N or whatever, then all these languages are at least as hard as L in terms of efficiency. That would mean that all these languages are not solvable in polytime. Cool. So if we could just kind of show that L is not solvable in polytime, it's like a domino effect, right? So Haltz was the domino effect, like the first base case in your dominoes for the decidability world. And similarly, we can have like our first domino be L. If we were able to show that something wasn't solvable in polytime, then that could be like a domino, which shows that, and then if you have a bunch of reductions which stem from that something, then like all the other things, like these guys here, would also not be solvable in polytime, right? So you might be a little bit concerned by this. You might say, oh, L reduces to K. That means that if K is solvable in polytime, that L is solvable in polytime. But why would that mean that if L is not solvable in polytime, then K is not solvable in polytime? Consider the contrapositive of this. Right, so the contrapositive of this guy tells you that if A is not solvable in polytime, then B is not solvable in polytime, right? So it's exactly the same as what we did in the decidability world. To show that A reduces to B, you usually show this statement directly, that B solvable, A is solvable. But really the reason we do these reductions is because the power in them comes from their contrapositive. Cool. So this is a little bit of motivation for why we're going to develop the machinery that we're about to develop. And specifically the machinery we're about to develop are polytime reductions. Cool. So like I said, there's going to be two polytime reductions that we talk about in this class, two different kinds. The first kind is called Cook reductions. And now these are what you would usually imagine are the more useful kind of reduction, and these are going to be the ones that are more intuitive. For reasons that aren't going to be very evident now, maybe not even by the end of this video, Cook reductions are actually not the move. We're going to want to use something else called Karp reductions. But it's still important to know what a Cook reduction is. And I'll try and give some intuition later in this video as to why Cook reductions don't work, even though when I introduce it, it's definitely going to seem like Cook reductions are what we want. Cool. So what is a Cook reduction? We say that A Cook reduces to B if given a polytime decider for B, we can create a polytime decider for A. That seems reasonable, right? That seems like exactly the same as a Turing reduction, except now we're just kind of making sure that our oracle for B is polytime and that the overall algorithm we build for A is also going to be polytime, right? Cool. So that seems reasonable. So what is a Karp reduction? So first, I'll give you the formal definition of what a Karp reduction is, and then maybe we can talk about what it's really doing and how it's different and why it might be useful. So the formal definition for a Karp reduction is, so basically what it's going to be is it's going to be like a Cook reduction, except you can only call the oracle for B exactly once, and you must return this output. So not negated. Right? So a Cook reduction might look something like this. Define MA, you take in something X, you do a bunch of stuff, you run MB on X, maybe you do some more stuff, you run, or some Y, you run MB on some other string Z, etc. You keep doing stuff, and then you make a decision. Right? Notice that we've run like the oracle for B multiple times here. And maybe like your last line was like run MB on like W and then like negate the output or something like that, right? It might be something like that. Note that like multiple uses are okay, but still like a polynomial number of uses. Otherwise, our decider for A isn't going to be polytime. Cool. So a Karp reduction is going to look kind of similar, except it's always going to look like this. Define MA on X and do a bunch of stuff, right? Let Y be the result of doing a bunch of stuff. And then we're going to return MB on the string Y, right? And we're not allowed to negate here. Negation not allowed. Cool. So every Karp reduction kind of looks like this. It's you take in a string X, you do a bunch of stuff to that string X, and eventually you get the string Y. And then you just return the oracle for B, its output on that string Y. Cool. So that's interesting. I'm going to delete this, and we're going to talk more about Karp reductions. Cool. So I still haven't given you the formal definition for Karp reduction, although I guess from that you could kind of formalize it. But what I want to make very clear is that every Karp reduction basically looks like this. So you define MA on X, and then basically what you do is you transform X, right? We did a bunch of stuff when we got that string Y. So you transform X using some function f, right? And this function f has to be polytime computable. And then you run MB on Y and return the output, not negated. Again, just the plain old output, right? So if every Karp reduction looks like this, right? It's exactly of this form. Then there isn't really a need to write it out in this way every single time, right? So a Karp reduction, again, it's just a specific kind of Cook reduction, but we're only allowed to run the oracle once, and we have to just output exactly what the oracle told us. If the oracle said yes, we have to output yes. Cool. So it seems like the only interesting part about a Karp reduction is this polytime computable function f here. Cool. So let's talk about this polytime computable function f. What do we need? We need f to be 1, polytime computable, and it should satisfy the following. If x is in A, that implies that f of x is in B, and if x is not in A, it should output something that is not in B. Cool. Right? In other words, this polytime computable function f, it should map yes instances of A to yes instances of B and no instances of A to no instances of B. Cool. So when we specify a Karp reduction in this class, all we'll ask you to do is present a polytime computable function f. We won't ask you to write out all of this because that would be unnecessary. You'd be doing that same writing out this line, and this line every single time, right? So all we actually ask you to do is to present a polytime computable function f, right? So important. Steps to showing that A Karp reduces to B. This is a P over here. Steps to showing A Karp reduces to B. Step 1, you present a function f. 2, you argue that f is polytime computable. Step 3, you show that x is in A if and only if f of x is in B. You can think about this as 2 steps if you want, because there's 2 implications. Cool. So here are the 3/4 steps to showing that A Karp reduces to B. Cool. So this was some machinery that's going to be important for when we talk about some more interesting stuff. So now what we're going to do is we're going to change gears and we're going to talk about completeness and hardness. Cool. So what does it mean for a language to be hard, or what does it mean for a language to be complete? So a language, we say that a language is C hard, where C is some complexity class. Example like NP. A language is C hard if we say that for all languages K and C, we have that K Karp reduces to L. So we say that L is C hard if for all K and C, K Karp reduces to L. So that's a lot of like terminology, it's a lot of weirdness. Let's maybe break this down into something more Englishy, right? L is C hard if L is at least as hard as every language in C. And when we say at least as hard, this means with respect to Karp reductions. Cool. So this is what it means for a language to be C hard. Now, what it means for a language to be C complete, this happens when 2 things happen. One, L is C hard, and the other, L is in C. So when I say that a language is C complete, for example, NP complete, that means that the language is in NP and it's at least as hard as every other language in NP, right? So you can think about something being C complete if and only if it's kind of like one of the hardest things to solve in C, right? So this means that L is one of the hardest things to solve in C. Cool. So that's interesting. This means that every language in C reduces to L, right? So L is like the hardest thing to solve in C. Now, if we showed somehow a really smart algorithm to show that L can be solved in polytime, that would imply that every language in C is solvable in polytime. That's pretty neat, right? If we showed that L is like C complete and L is solvable in polytime, that means that every language in C is solvable in polytime, which would mean that C is a subset of P. So now you might be thinking back to like that $1 million question about like P versus NP, if P is equal to NP. So how could we show that NP is a subset of P? If we wanted to show that NP is a subset of P, and thus P equals NP, what we need to do is we need to come up with a language L, such that L is NP complete. And 2, we need an algorithm to show that L is actually in P. This would imply that NP is a subset of P, because every language in NP would reduce to L, right? L would be in P. That means every language in NP would also be in P, thus showing this containment. Cool. So now this is kind of weird because we've been talking about NP without even giving like a formal definition of what NP is. So let's get into like kind of the weeds of what NP is, but hopefully like by now, like the overarching picture should hopefully make sense about like what we're doing here, why we have Cook and Karp reductions, etc. Again, maybe it might not make sense, like why we're using Karp reduction specifically instead of Cook, when Cook really seems like what we should be using. But again, I'll motivate that maybe in a little bit. And if I don't get around to it, then it'll definitely be on your homework. Cool. So let's talk about chapter 11 a little bit now. And this is the complexity class NP. So the very first comment I want to make, because I see this every single semester, NP is not the same, is not polynomial. As I said earlier, P is a subset of NP, so this doesn't even make sense. Cool. NP stands for non-deterministic polynomial. And maybe you know what non-deterministic means, maybe you don't, and you might still be confused. You might be like, okay, why do we call it non-deterministic polynomial? That's something that maybe we'll talk about later. But for now, I'm not going to motivate this name at all. Just remember, non-deterministic polynomial just basically means kind of like efficiently verifiable, right? So let's talk about what NP really is. So NP, L is an NP, a language L is an NP, if there exists a polytime, let's call it a verifier. It's really just kind of like an algorithm, which we'll call V, and a universal constant, K greater than 0, such that for all x in L, there exists a U, right, in sigma star, such that the length of U is less than or equal to the length of x to the k, where Vxu accepts, and for all x not in L, for all U in sigma star, Vxu rejects. Okay, so this is a mouthful. This definition is a lot to take in, right? We're saying that a language is an NP if there's a verifier, which takes in two inputs, x and u, and a constant k, such that these two properties are true, right? So what am I trying to say here, right? X, this is your input. This u here, we like to call it a witness or a proof, right? So what you can think about this verifier is really doing is if an input is a yes input, if you have an instance and that's a yes instance to the language L, right? That means that if you gave me a solution, right? Like a solution that proves that X is actually an L, aka if you gave me a U, I would be able to, or the verifier would be able to, in polytime, tell you, hey, that solution checks out. I guess X actually was an L. Cool. So basically, if something is an L, there exists kind of like a poly-sized solution, right? That proves that, hey, X was actually an L. But if X is not an L, then there's no way to trick my verifier into saying that, oh, X was actually an L, right? Like, if X is not an L, no matter what kind of proof you give me, my verifier will be like, nah, that proof doesn't check out. I don't believe you when you say that X is an L. Try again with a better proof, right? So if X is an L, there's some way to prove to my verifier that X is actually an L. But if X is not an L, there's no way to prove to my verifier because there's no proof of a false fact, right? Cool. So maybe it's important to kind of like take a step back and really think about this definition because there's a lot of stuff going on, right? So there's a couple things I want to highlight. First of all, this universal constant K is fixed here, right? It's a verifier and a number K, right? This K cannot go over here. If the K goes over here, right? If I say something like for all x and L, there exists a K greater than 0, there exists a U in sigma star such that blah, 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 right? And then stuff goes seriously wrong. Because if I can choose a K for every single x, then we have a problem, right? Because now I'm not really enforcing that my U is actually poly-sized anymore. Cool. So that's one issue, right? So like notice that this witness and proof has to be kind of like poly-sized with respect to x. And notice that this K has to be fixed with the verifier itself. So maybe this isn't very clear. Maybe I can make this a little bit more clear. I'm going to erase this because I don't know how to make a new page yet. I apologize. Cool. So let's say that we have x length and the length of a u necessary to kind of prove that x is an L. Let's say when x length is like 2, u has to be size 4. When x length is 3, u has to be size 8, 4, 16, 5, 32, 6, 64, and so on, right? So now, if the constant k can be chosen, right, for every single x, then what goes wrong, right? So clearly the trend here is that like the size of u is equal to like 2 to the size of x, right? So the size of u is not like poly-sized. We can't say that we have like a poly-sized certificate that really proves that x is in the language, or when x is actually supposed to be in the language, right? But clearly this trend is like it's going up by like a factor of 2 every single time, right? But the problem here is that if I'm allowed to choose a k for every single x in sigma star, right, then I can look here and be like, oh, choose k is equal to, I don't know, 2. Oh, k equals 2 still works. Here, k equals 2 still works. I guess I'll use k equals 3 this time. And then 6 to 64, okay, k equals 3 should still be fine, etc., right? And my k's will be growing. Basically what I'm trying to say is like for any specific number and another number, I'll obviously be able to find you like a k that works so that like the first number to the power of k is bigger than the second number, right? That doesn't mean that something is polytime or poly-sized rather, because polynomialness, like polynomial size, polynomial timeness, these are all kind of properties of like, you need to have a fixed constant that kind of pervades, what's the word, that kind of like goes over kind of all of the inputs, right? You can't just have like a constant for every single individual input, different constant for every individual input. That's why the k needs to be universal to the and fixed with the verifier itself. Cool. Let's go ahead and erase this now. And now we have the definition of NP, right? So a couple things that maybe we should talk about is, what do we know about NP? Well, the first thing we know about NP, like I said, was P is a subset of NP, right? And why do we know this to be true, right? Let L be in P. How can we come up with a verifier for L with the required specs? So specifically what your verifier can do is it can take in an x and a u, and it kind of just can ignore u, and it can like solve to see if x is an L, and this is doable in polytime since L was in P. And if yes, output true. If no, output false. Cool. So with this definition, it should be clear that kind of every language in P is also in NP. Awesome. Let's maybe give an example of another kind of like way to show like a language that you know is in P. So let's look at the language example of 3-color ability, right? You may or may not know this already, but 3-color ability is not actually a very easy problem to solve efficiently. However, it is a very easy problem to verify efficiently, right? You can define V, and then your input would be like some graph, and then you'd have some witness U. And then what you can do is you can be like, hey, if U is an encoding of, or let's say it's not an encoding of vertices in G mapped to colors red, green, and blue, right? Then reject. And then your next step can be check that no edge in G has 2 vertices of the same color. If good, you accept, else you reject, right? So what's the intuition here? 3-color ability is clearly like in NP. Why? Because all we really have to do is if we're given a solution, we can check, hey, you color the graph correctly. There doesn't seem to be a constraint violation there. So hopefully that's a little bit of a like intuition with how we can show that something is an NP. Right, so everything in P is an NP, and then if you have something that's like a constraint satisfaction problem like circuit sat or 3-call or 3-sat, your witness or your proof that something is actually a yes instance can be like the correct way to color the graph or the correct way to assign variables to true or false. Cool. Let's also talk about this complexity class exp, right? These are things that can be solvable in exponential time. So specifically, it's like O of 2 to the n to the c for some constant c. NP is actually a subset of exp. And the way you can show this is let L be an element of NP. We want to show that L is also an exp. So if L is an NP, this implies that there exists a verifier V and a constant K greater than 0 with the required properties, right? Such that if X is an L, blah, blah, blah. If X is not an L, then blah, blah, blah. So how are we able to solve L in exponential time? Cool. So since we know that if X is an L, it must have a poly-sized witness, I'm going to write here, poly-sized witness makes V accept, right? And here, no witness makes V accept. Just a quick side note. So for the X not an L case, we said that for all U in sigma star, we could have also said for all poly-sized U. But there's no really reason to make the definition like that. But no witness makes V accept if X is not an L. Cool. So to check whether X is an L in exponential time, we can try running V on every single possible witness, right? So to solve L in exponential time, run V on every single witness. If any accept, then accept. Otherwise, reject. Cool. So that's showing that NP is contained in exp. Cool. So just a couple more things before we talk about the real cool theorems here and get into like the last part of this whole video. A couple more things that I want to say is halts. Is halts in NP? Question mark. So it seems like halts might be an NP. You can come up with a verifier, define VXU. X can be parsed as like some Turing machine M, and some, I don't know, some input, let's call it Y. And then U, you can think about U as kind of like how many steps it takes M before it halts on Y. And then you could try doing something like run M on Y for U steps. Cool. So this seems like a reasonable verifier for halts. So maybe halts is an NP, but you're right that this is broken because if halts was an NP, that means halts was an exp. And if you're exponential time decidable, that means that you're also just decidable. We know that halts isn't decidable, right? So why is this wrong? The reason why this is wrong is because we have no upper bound on how long it would like, on how like large this U possibly could be, right? Like even like a baby Turing machine and a baby input, it might take a 1 trillion steps for it to actually halt, right? It's not necessarily going to be like growing at a poly time rate. Cool. So that's why halt isn't an NP. I wish that I was able to do this interactively because then I could answer your questions as we are going along. Cool. Again, if I'm going too slowly, I hope you've been skipping around and watching this on 1.5 times speed. And if you're confused about anything, I encourage you to kind of like rewatch some sections or to leave comments, and I'll try and kind of clarify any confusions. Cool. So the next thing I want to talk about is kind of the cool part, and this is what everything's been leading to so far. So far we've talked about like polynomial time reductions. We've given the definition of NP. We've kind of shown like examples of what's an NP. We've shown NP is contained in X. We've shown P is contained in NP. And we've kind of talked about like this notion of hardness and completeness, right? Abstractly, we talked about what it meant for a language to be NP complete. But what we haven't talked about so far is whether we know of any NP complete languages, right? We actually do know of one such language, and well, we know of a bunch, but what I'm going to introduce now is something called the Cook-Levin theorem. And specifically what this is it was a proof by Cook and Levin independently that SAT, or for the purposes of like this, yeah, let's just go with SAT. SAT is NP complete. So maybe I shouldn't put this element symbol there. It's not a big deal. SAT is NP complete. And this is an awesome theorem. You don't actually need to know the proof of this theorem. The proof of circuit SAT is NP complete or SAT is NP complete is in the notes if you're curious. But since we haven't studied like Boolean circuits this semester and we won't be studying it, it might be a little bit confusing. What you need to know is that this kind of proof exists as a black box. And this is now really awesome because we've now shown that a language in NP is NP hard. So SAT, recall that this means that SAT is in NP and SAT is NP hard. Cool. In other words, for all L in NP, L Karp reduces to SAT. So why is this awesome? What I may have neglected to mention is that Karp reductions are transitive. So if I know that A reduces to B and B reduces to C, intuitively, and this is true, it should be true, that A reduces to C. This is in fact true. Cool. So now, if we wanted to show another language was NP complete, right? Or NP hard, let's say. If we wanted to show another language was NP hard, let's say want to show K is NP hard. We can do one of two things. Either show every language in NP reduces to K. When I say reduces, I mean Karp reduces. Or just show that SAT reduces to K. Because if we put a little PMK right here, this means that every language in NP reduces to SAT by this transitivity. Cool. So yeah, Cook-Levin did something amazing. What they did is they basically did the equivalent of what like Turing did with Hals, right? They came up with that first like domino, and now by kind of like connecting languages together based on their like polytime difficultiness, we're able to kind of show that a lot of other languages are NP hard. So as a result, we get as a result that a bunch of languages are NP hard through these reductions. And more importantly, not only are a bunch of languages NP hard, a lot of these are in NP too. So we have a bunch of NP complete languages. And now this is kind of like a bunch of tools in the arsenal of an algorithm specialist who now wants to prove that P is equal to NP. Because they can just kind of pick out any of these NP complete languages that we've shown exist. By we, I mean like the complexity theory folk. I don't claim to be one of them. But an algorithms person can now pick out one of these NP complete languages, come up with a polytime algorithm for that language, and in the process be showing the existence of a polytime algorithm for literally every single language as an NP. So if you come up with an efficient way to solve an NP complete language like 3-color ability, now congrats. We have efficient ways to factor, to solve 3-SAT, to do basically any problem that you thought of is an NP, right? If you come up with a cool algorithm for just one of these NP complete algorithms, problems, then you have a cool algorithm for basically every single problem in NP. Now that's awesome. Cool. So this is kind of like the high-level points that I wanted to talk about. I'll spend the remainder of this video kind of going over some common misconceptions, slash just kind of talking about like some important things to know as well. Cool. Cool. So the first thing that I want to talk about right, is halts is NP hard. I'm not going to say exactly why, because you need to actually show that halts is NP hard in your check the understandings for this week's homework, but you should think about why. Some other things is that, is there anything more that I really wanted to cover? See, this is the part where I'd really appreciate having student feedback as I'm doing this. Cool. Okay, so now I think I know what I want to talk about. The last thing I kind of want to leave you guys on is kind of maybe slight motivation for two things. The first thing I'll talk about is why Karp and not Cook. So the reason for this is you might have noticed this kind of like this lack of symmetry in the definition of NP, right? Like if X is an L, then there exists a U. But if X is not an L, then for all U, something is true, right? So this lack of symmetry kind of is interesting, right? Like if I were to flip these things here, then I would get actually a different complexity class. So right now, it's a complexity class NP. If I flip and I make it like if X is an L, then for all U, blah, blah, blah. But for if X is not an L, then there exists a U, blah, blah, blah. If I flipped it like this, then I would get a different complexity class called co-NP, right? And as it turns out, Cook reductions can't capture the difference between NP and co-NP. Why can't they capture the difference? Because they let you flip the output. Karp reductions, remember, you're not allowed to negate the output, right? So this is why we use Karp reductions. The reason we use Karp reductions is because most people believe that co-NP is not equal to NP, right? So we want to be able to kind of capture the difference between the lack of symmetry in these definitions. Cool. So I would say more about this, but I don't know how much is actually going to appear on homework. So I'm going to stop there on that. The second thing I want to talk about is like maybe just kind of philosophically. So we know that a bunch of languages are NP complete, 3-call, 3-sat, etc. These are all NP complete. However, 2-call, 2-sat, etc. These languages are all in P, and we know algorithms to solve 2-colorability in P. How do we solve 2-colorability in P? You just check that the graph has no odd cycles. Remember, 2-colorability is the same thing as bipartite, and so you're just checking whether the graph has no odd cycles. That can be done in polytime. So if 2-colorability is so easy to solve, then why isn't 3-colorability also easy to solve? Well, the reason between that is it's not really the difference between the number 2 and the number 3. It's really the difference between the number 1 and the number 2, right? When I make a decision to color one vertex, like let's say green, because I did so, and the other color I have is red, then like if I think about if I color this vertex green, then I only have one option left here. This is like the 2-call case, right? Cool. Now in the 3-call case, right, if I were to color a vertex green, and now I'm wondering what to do with like its neighbor vertex here, I'm going to have two options. I can do blue or red, right? So the difference between 3 and 2 is really the difference between 2 and 1. And this is something I think confuses students a lot. So I just wanted to kind of highlight why maybe like languages like 3-call and 3-sat are NP complete when languages like 2-call and 2-sat are actually NP. Cool. So I might have missed some stuff. If there's anything else you'd like me to go over, if there's any part of this video that was kind of unclear, I apologize. I'm doing this for the first time. I'm really not comfortable with this iPad yet. Please comment, let me know. I'll try and clarify anything that I can. Otherwise, thanks for watching. I hope this was somewhat helpful, and see you on lecture on Thursday. Thanks, guys.